This is going to be incredibly affordable. Just as people were saying, Elon Musk confirmed the expected cost of the Tesla Model 2 and then showed how sure he is about the design. It's an unbelievably good design. The Tesla engineering team is just amazing. But what does all that really mean for an electric car priced at just $10,575? How exactly did Tesla create the new Tesla Model 2? And will it truly offer us practical value in our daily lives? Inside the Model 2, Tesla has quietly blended the very precise driving feeling of a Porsche 911 with the smooth, flowing shape of a Jaguar F-Type, resulting in a small car that is surprisingly good in both quickness and comfort. The famous Falcon wing doors, designed to work well in very tight parking spots, seem easy to use even on this low-cost model, while the latest gigacast underbody structure makes sure the ride remains comfortable and steady at fast highway speeds. And we are going to tell you how they achieve these seemingly impossible designs today and show how Tesla transforms a big, brave idea into real-world engineering that actually works. So if you are curious to know more, please hit the subscribe button and ring the notification bell and join the 239,777 people already following the most recent information and insights about Tesla. First, how did Tesla manage to bring together the qualities of a Porsche 911 and a Jaguar F-Type into a compact vehicle costing only $10,575? When you look at Tesla's Model 2, you can almost feel a strange sense of familiarity with the sharp, accurate feel of a Porsche going around a corner, but also the balanced, elegant look of a Jaguar side view. Yet it also feels completely new. The question that is really exciting every engineering discussion group right now is this: how did Tesla put that high-end, premium driving soul into a car that costs less than most electric bicycles you find in Los Angeles? Tesla used what they call internally scaled dynamics. They weren't just copying the chassis numbers of a sports car, but rather they were scaling down the 911's concept of a low polar moment, how the car rotates around its center, and the F-Type's long, graceful look into a smaller package. Their main goal was to reduce the rotational inertia by about 10% to 15% compared to other similar cars in the same class. This is what keeps the steering feeling quick and responsive without the nervous, jumpy feeling that makes many sports sedans potentially unsafe for regular drivers trying to merge onto the busy I-95 during the evening rush hour. The way the car's weight is spread out really tells the whole story. Tesla aimed for a weight split from front to rear that is very close to 48% in the front and 52% in the rear, meaning the back is slightly heavier. This helps achieve that perfectly neutral steering feel that reminds you of a 911, while still maintaining predictable behavior for drivers who simply want to go buy groceries without having to struggle with the steering wheel. They achieved this precise balance by positioning the battery modules slightly towards the rear and adjusting the weight of the front subframe using roughly 55.1 pounds of carefully placed weights and structural parts. This wasn't a guess, it was a calculated placement of mass that actually changes how the car pivots and turns through corners. The Model 2 is designed with a longer wheelbase in relation to its total length than most typical compact cars. We estimate the wheelbase is increased by 6 to 12 inches compared to others in its category. This design makes the highway ride much smoother for older drivers enjoying a long drive across Arizona, while keeping the car easy to maneuver in the small, tight parking spots common in places like New York and California. Tesla thoughtfully looked at how people in America actually drive and built the car's size and shape around those real-life needs. The suspension plan shows where Tesla decided to be very strict about efficiency. They combined the progressive anti-roll geometry, similar to a Porsche's, which resists the car lifting under side loads, with the multi-link comfort tuning often found in a Jaguar. They reduced the spring stiffness by roughly 15% from what a purely sport setup would use. To balance this, they increased the stiffness of the anti-roll bar by 10% to maintain good body control without making the ride feel too harsh. The final outcome is a suspension system that feels firm and steady on the highway, but is still very forgiving when you hit those terrible potholes in Chicago at 3 o'clock in the morning. The steering gear ratio shows that Tesla really understands American driving habits. They chose a ratio that is about 10% quicker than the average compact car, but then they added software damping to prevent any nervousness or sudden movements. This allows for confident, easy lane changes on fast Texas highways and gentle, smooth corrections for drivers in New York trying to back into a tiny parking space that's barely wider than the car itself. The steering doesn't fight you, it seems to anticipate what you need. Aerodynamics are far more important than most people realize. Instead of adding extreme sports downforce, which dramatically reduces the car's driving range, Tesla aimed for a low drag coefficient of around 0.2 to 0.24, while using very slight adjustments at the rear to control lift for good stability at high speeds. On a long touring journey between seaside California towns at a speed of 65 miles per hour, simply improving the drag from 0.26 to 0.23 saves approximately 8% to 12% of energy. For a car with a standard range of 2 to 50 miles, that means an extra 8 to 12 miles of range. For older drivers who worry about running out of battery on those long retirement road trips across Florida, Those few extra miles can be the difference between reaching the next charging station or having to call for help on the side of the road. Inside the car, Tesla copied the approach used by Jaguar for the feel of the controls. They used thicker door handles and positioned the dashboard sills lower. These details give a feeling of high quality without actually needing to use expensive materials. By using selective molded foam and high-quality synthetic leather alternatives, they recreated the premium feel of an F-Type, but at a much lower material cost. Your hand won't be able to tell the difference between expensive $80 per yard leather and $12 per yard synthetic material when the texture, softness, and firmness are matched within a tiny 3mm margin of difference. The first time you ever felt a Porsche grip the road perfectly through a curving mountain pass or experienced the quiet confidence of a Jaguar effortlessly gliding down a main boulevard. Tesla studied the emotions those cars made the drivers feel. The lightness you feel when turning, the immediate response when you push the car. Instead of just borrowing little design parts, they completely re-engineered that feeling from scratch using their pure electric vehicle platform. Every curve, every small placement of weight in the Model 2 was finely tuned not to just look like a premium car, but to bring out the same powerful emotional connection that makes you smile when the road stretches out open and clear in front of you. Now, let's take a moment to consider something. If you had to choose just one engineering priority for an electric vehicle that is both budget-friendly and still has good performance, what would matter to you the most? Type the number 1 for steering precision, which makes every turn feel perfectly connected to the road. Type the number 2 for suspension comfort, which easily soaks up real-world bumps and damage on the road without making the car feel too soft or floaty. Type the number 3 for aerodynamic efficiency, which significantly extends the car's driving range without sacrificing high-speed stability. Please drop your number in the comments section below. This will help us know what drivers truly value, as opposed to what car makers think we want. However, even the most brilliant engineering in the car's main structure and dynamics means nothing if the doors can't even open properly in your garage. Tesla's next major obstacle seemed truly impossible, fitting the complex Falcon Wing doors into a vehicle that absolutely must cost less than $11,000. The original Model X almost caused the company to go bankrupt trying to perfect that complicated door mechanism. So, how did they solve the cost problem without turning the Model 2 into a simple, stripped-down compromise? Let's find out in the next part of our discussion today. Second, how did Tesla successfully incorporate Falcon Wing doors into a low-cost electric vehicle without completely ruining the budget? When you see those doors swing open, your immediate thought is that this simply cannot be cheap. But it's not just a fancy trick, it's Tesla solving a very common, real-world problem in a way that no other car company has even attempted. Think about very narrow parking spaces, older passengers who struggle to get into or out of a car in a tight spot, and unexpected bad weather. Tesla looked at all these daily difficulties and designed a solution that is both incredibly elegant and highly practical. So, these are the important questions we need to ask. How did Elon Musk ever approve a door design this complicated for the very lowest cost Tesla ever produced? And how did his brilliant engineers actually make it work without completely exceeding the strict budget? The key to this success lies in engineering that is focused purely on the door's main purpose. Falcon Wing doors offer a real, measurable benefit in tight spaces, providing an estimated extra usable shoulder clearance of 16 to 24 inches compared to a normal car door. That measurement might not sound like a huge difference, but for older passengers or for someone carrying heavy bags of groceries, it means much less twisting, far less physical strain, and a significantly smoother entry or exit from the vehicle. Tesla dramatically simplified the mechanism for the door hinge. Unlike the multi-axis, completely motorized system used in the expensive Model X, the Model 2 uses a hybrid system that relies on mechanical counterbalances, assisted by a single electric motor and special over-center dampers, a technology inspired by the doors on small, light aircraft. This clever design cuts the power requirements for the motor by up to 60%. It also reduces the total number of parts needed by approximately 40% compared to the complex Model X system. Component costs were further lowered by replacing the expensive aerospace-grade aluminum parts with stamped high-strength steel covered with bonded composite materials, which is estimated to reduce the cost per door by about 30% to 45%. When you combine this with a simplified electronic control setup that uses only a single controller, the extra cost added per door is in the low triple-digit dollar range, instead of thousands of dollars. The weight and how that weight is balanced were managed with extreme care. Door skins and internal structural supports were aerodynamically designed and made hollow to keep the weight of each door within a strict budget of 26 to 40 pounds. This is crucial for maintaining the car's center of gravity targets and preserving the precise handling characteristics. Tesla likely used the same standardized door actuators across different models, which helps lower the cost of spare parts and repairs, a detail that both older drivers and owners who are careful with their money will certainly appreciate. Safety is also naturally built into the door's physical design. The higher door opening allows passengers to step down into the car rather than having to twist their body, while the clever door seal design limits rainwater intrusion to around 0.26 gallons per minute even during heavy highway spray conditions, keeping the cabin dry during severe storms in places like Florida or New York. Just imagine yourself parked tightly between two huge pickup trucks in a very crowded Texas supermarket parking lot, holding a heavy bag of milk, maybe with a slightly aching back. You simply press a button, and the door quietly lifts straight up instead of swinging wide open. No risk of door dings, no difficult squeezing in. These are the small, everyday moments that make the Model 2 feel like it was truly designed for the needs of real people, not just for maximum profits. And the real genius is that Tesla achieved all of this with mechanical components simple enough to keep maintenance costs low and affordable for many years to come. But a premium, clever door mechanism is completely meaningless if the structure underneath it feels like it's going to shake itself apart on a bumpy road. Gigacasting promised a huge, revolutionary leap forward in manufacturing speed and cost savings by molding entire vehicle sections as single pieces. However, a significant issue arose during the early testing phases. The first prototypes showed an unusually harsh, stiff ride quality and strange, persistent shaking that the engineers couldn't figure out for 3 long years. Tesla's ultimate solution didn't just fix the problematic vibration, it completely changed how large, single-piece cast aluminum structures behave when subjected to real-world driving stress. Third, how did Tesla completely solve the problem of the car feeling unusually stiff and shaking? Interestingly, when it comes to gigacasting technology, some of you were absolutely right to be concerned that even though gigacasting reduces overall weight by 20%, there is a high chance of small casting flaws that could lead to abnormal stiffness and very strange vibrations at high speeds due to the alloy's composition being uneven. Tesla definitely encountered this exact problem. Their engineers spent 3 frustrating years trying to track down these mysterious vibrations that would only appear when the car exceeded 65 miles per hour, disappear completely during slower testing, and simply could not be reliably reproduced in a consistent way. So how did they finally find the solution? Extremely controlled alloy chemistry became the absolute foundation of the fix. Every single critical element in the aluminum alloy is now strictly held within a very tight tolerance of plus or minus 0.5%. This incredibly precise control ensures that the material's elastic modulus C, its stiffness, is uniform throughout the entire casting. An uneven composition in the alloy creates localized variations in stiffness, which show up as dead spots or high-frequency vibrations when the car is being driven dynamically. A section of the casting that is just 2% harder than the design intends acts like a completely rigid plate, sending road shock directly into the cabin, instead of absorbing and dampening it. By controlling the chemistry this precisely, Tesla guarantees that no section of the casting is significantly harder or softer than planned. The metal then behaves exactly as predicted under stress, which means the suspension engineers can tune the damping perfectly without having to fight against unpredictable flexing in the car's main structure. The vacuum-assisted die casting combined with directional solidification was used to completely eliminate the common problem of porosity, tiny air bubbles. Tesla now pours the molten aluminum into the mold while under a vacuum, which drastically reduces the amount of trapped air and shrinkage voids. Directional solidification then pushes any small amount of remaining porosity towards areas that are not critical to the structure, such as edges or internal cavities. This process reduces the porosity in the high-stress zones from a typical 1% to 2% down to 0.2% or even less by volume. Those very tiny air pockets act like microscopic springs that flex differently from the solid metal surrounding them. Above 65 miles per hour, vibrations from the wheels in the range of 15 to 20 Hz hit these voids and create a noticeable resonance that makes it feel like the entire car is shuddering. By eliminating these voids, they eliminated the unwelcome resonance. Post-cast homogenization and heat treatment are used to make the grain size consistent and relieve the intense internal stresses that are locked into the metal during the quick cooling process. Any dimensional changes are kept very small, less than 0.020 inches on key surfaces where things are mounted. Suspension connection points and body mounts remain perfectly consistent, with tolerances that are tighter than a single human hair. If these crucial points were uneven by even a small 0.50 inches, you would immediately feel variations in stiffness through the car's body and steering. One corner would feel perfectly planted and stable while the opposite corner felt loose or disconnected. Tesla's specific heat treatment cycles prevent this kind of production inconsistency from ever reaching the customer's vehicles. Next, targeted structural reinforcement shows how smart Tesla was about trading off weight for stiffness. They added pressed and high-strength steel inserts and bolted on ribs in only 10% to 20% of the underbody structure, placed precisely at the areas that experience the highest bending or twisting stress. The remaining majority of the casting stays light, preserving the significant 20% weight savings compared to a traditional floor made of many stamped parts. This combination ensures uniform, overall stiffness without adding unnecessary weight that would negatively affect acceleration or reduce the driving range. The result is a floor structure that resists twisting and flexing when cornering hard, but doesn't weigh so much that performance suffers. Noise, vibration, and harshness. NVH control is the most critical element of all. Engineers discovered that people are most sensitive to subtle shaking in the 20 to 30 Hz frequency range at highway speeds. That specific frequency naturally matches the natural resonance of the human chest cavity, which is why it feels so uncomfortable even when the actual vibration is very small. Tesla strategically placed special elastomer isolators and tuned mass dampers at the key mounting nodes where forces are transferred, reducing the vibration amplitude by roughly 70% in that sensitive frequency band. These dampers essentially act like tiny shock absorbers for the car's structure itself, breaking up the resonance before it can ever reach the cabin. This is why drivers do not feel the unsettling shivers that older aluminum castings might produce when cruising comfortably at 75 miles per hour across the flat roads of Nevada. Quality control now catches any defects long before they ever reach customers. Every single casting is scanned using ultrasonic testing to detect any porosity greater than 0.15%. Thermal imaging is also used during the metal's solidification phase to check for uniform cooling. Any casting that is outside the exact specifications is automatically removed and sent for recycling. Tesla now achieves a defect rate of less than 1 per 10,000 parts for the areas critical to the car's stiffness. Compare that to traditional car assemblies where inconsistent welding can create weak points in as many as 1 out of every 500 units. The huge difference will become clear 5 years from now when one car starts developing a squeak or creak in the floor structure while another remains perfectly silent. Are you still slightly doubtful about how Tesla can engineer this incredible level of structural integrity into a vehicle priced at just a $10,575? If you now believe that this proves affordability does not have to mean accepting compromises, type $10,575 in the comment section right now. The Tesla Model 2 has successfully proven something that the entire industry said was impossible to achieve: high-level performance engineering, genuinely practical innovation, and fundamental structural integrity, all at a price point that was supposed to require many compromises. How do you feel now about Tesla's engineering capabilities? Is there any other incredible breakthrough you would like to see them achieve next? Please drop your feelings and ideas in the comments, and we will catch up with you in the Everyday Community tab. Our next video is scheduled to drop in 12 hours. Make sure you do not miss it.